All right, we have a simple harmonic motion problem here. We're going to look at a mass spring system, and we're going to do an example for it. So I do have a spring with a spring constant of 12 newtons per meter. I went ahead and I put a 1.2 kilogram mass on a frictionless surface, and I've compressed the spring 5 centimeters. And I'm going to do two things. I'm going to first derive a position versus time equation for this mass as it oscillates back and forth on that connected spring. And I want to figure out what is the maximum velocity that mass will reach. And I'll give you a couple options for how to find that max velocity. All right, so the first thing I need to do is derive a position versus time equation. So what I'm going to start with is I'm going to start by summing up the forces in the x direction, setting equal to ma. And there is only one force in the x direction, and that is the force from the spring, which is equal to negative kx. And that's because the position and the force will be opposite. So really this is a vector position here. Equals ma. Now, I do see that I have m and k, which are going to be constants, so I have an acceleration that's proportional to the negative of my position. That's a clue, okay? And if you want to see why that's a good clue, go down in the description. There is a link to general simple harmonic motion setup. Go ahead and watch that. That'll explain what we're going to do there, okay? So I need to choose to use x is equal to an amplitude cosine omega t plus phi. So this is my position function I'm going to use because acceleration is proportional to the negative of the position. Now I'm going to take this one step further, and I'm going to say the acceleration is equal to negative k over m times x. And you're going to, if you go back to the setup one link down in the description, you'll see that this matches the format I want of negative omega squared x. So I know that my omega value is equal to the square root of k over m. My spring constant being 12, my mass being 1.2. All right. So I know the omega value. All right. So now I need to also find out what is the amplitude. What's the maximum displacement? So if I displace it 5 centimeters and release it, it's never going to go further than that. I've put in a certain amount of energy, and it's not going to gain or lose any energy on this frictionless surface. So my amplitude is 5 centimeters. So I have x is equal to 0.05 times the cosine of my omega value, which is the square root of my spring constant divided by my mass, 1.2, times t plus phi. All right, I need a phi value, a phase shift. So the easy way to do this is to essentially plug in a condition. So for instance, I know at time 0 it should be at negative 5 centimeters. And so if I plug in negative 0.05 here, and 0 for time, and I solve for phi, you'll find out that you get a phase shift of pi. That is in the setup for how to set up a mass spring system and find the period. So if you want to see how I did that precisely, go down to the link in the description for setting up a mass spring system. All right, so now I have derived a position versus time equation here. All right, now find the maximum velocity. Okay, so maximum velocity, there's one of two ways I can do this. The key idea, though, is v is a maximum at the point where acceleration equals 0. So where will my acceleration equal 0? All right. So what we can go ahead and do is we can go ahead and take the derivative of our position function to get a velocity function, take the derivative of that, get an acceleration function, figure out when the acceleration is 0, and then plug that time in for v max. Okay, so let's see what that looks like. So v is going to equal the negative 0.05 times the square root of 12 divided by 1.2 times the cosine of, I don't need that parenthesis there, square root of 12 divided by 1.2 t plus pi. So there's my velocity function. My acceleration function then is negative 0.05 times 12 over 1.2, because this becomes squared then, times the, oops, that one is sine. I'm sorry about that. This is cosine down here of the square root of 12 divided by 1.2 t plus pi. All right, so I can go ahead and plug in 0 for the acceleration and solve for time. And then use that time in here and solve for v. But I want to tell you, there's a quick way to do this, like a sneaky buck trail, if you will. So when acceleration is 0, when is the cosine function 0? The cosine function is 0 at pi over 2. So all this stuff in the middle here is pi over 2, essentially. I don't know what the time is, but I know this section is pi over 2. That means that this section would be pi over 2, and the sine at pi over 2 is 1. And so the idea is that if I want to find the maximum velocity, essentially the maximum velocity is when the sine function is 1. And so what I can say then is V max is just equal to the amplitude times omega. That'll be the maximum speed. And so I can plug in those values. I can plug in 0.05 times the square root of 12 divided by 1.2 and find my maximum speed. And so we can plug that in quick here. 0.05 times the square root of 12 divided by 1.2. And you get 0.158 meters per second for a maximum velocity. There is a second way to do this. You can set up an energy problem here. Okay, you can talk about, all right, I have elastic potential energy at this point, and at this point, when x is 0, I don't have any elastic potential energy. I have all kinetic. And you can set that up by saying that 1/2 kx squared is equal to 1/2 mv squared. The 1/2s cancel. And so v is equal to the kx squared divided by m, take the square root, and you also end up with the square root of k over m times x, the exact same setup. So pretty cool. There you go.